So this is the 44th lecture, and I'll start with the numerical of half-wave rectifier based on half-wave rectifier, and there's a numerical problem here. I'm writing this as a numerical problem. Look at the statement of the problem. It says that a sinusoidal signal of 220 volt 50 hertz is applied to the primary of a 10:1 step down transformer used in a HWR, means half wave rectifier. First point is that. And if the diode has a forward resistance of 20 ohm and the load is used of 1 kilo ohm, then determine these values. One more thing I am adding here, rather fifth part of the problem, that draw the circuit diagram. Although even if it is not asked, you first must draw it. Draw circuit for given data, for given data, and also draw the input output waveforms. Input and output waveforms means signal waveform. So I am starting with this part first. A sinusoidal signal of this much 220 volt 50 hertz is applied to the primary of a 10:1 step down transformer used in a half wave rectifier first of all. So I have to draw the circuit diagram for a half wave rectifier, and I am drawing this circuit for a half wave rectifier, and the circuit is for half wave rectifier. You have a transformer here, just see. It is a transformer here. This transformer is being, this is a transformer, and this is a diode here, and then you'll have a load resistance. The simple diagram of a half wave rectifier. This is, and an AC signal is applied here at this transformer. So this is a transformer. Now again, coming back to the problem statement, it says that a sinusoidal signal of 220 volt and 50 hertz. Now just try to understand this. Is applied to the primary winding. This is the primary winding and this is the secondary winding of the transformer. It says 220 volt and 50 hertz is applied here, means the signal which is applied here is 220 volt and 50 hertz. This signal is applied here in the primary of a 10:1 transformer, means the turns ratio of this transformer is 10:1. Means if there are 10 turns here, it is 1 turn here. If there are 100 turns, 10 here. 1000, 100. So it is 10:1. Ratio is 10:1. Step down transformer used in a half wave rectifier. If the diode has a forward resistance of 20 ohm, this diode is having a forward resistance, I am writing here only, having a forward resistance RF of 20 ohm. The value of this RF, the forward resistance of this, it is not non-ideal one, means it is having some resistance, and the load resistance is 1 kilo ohm. I name this is my load resistance, I name this as RL. This is the load resistance RL, and this is given to you as 1 kilo ohm, or I can say it is 1000 ohm. This RL, you can say either 1 kilo ohm or this is 1000 ohm, one and the same thing. Then determine whatever is required. Now draw the circuit for the given data and the input and output waveforms. Now I am drawing the input and output waveforms also at the same time. Suppose I say that this voltage is Vs. Just try to understand this. This voltage is Vs, and the voltage, the input to this rectifier, this is a transformer. Rectification starts from this point. The rectification starts from this point. So here I assume as the input waveform Vi. Now I am drawing the waveform for this Vs as well as for Vi. So if I draw the waveforms for this, just see, it is very important to understand the problem. That is, if this is the waveform, suppose I say that I draw various waveforms at this point only. Initially, I am drawing for this Vs. This is for, first of all, this waveform is my for Vs. That is the supply voltage here. This is 220 volt and 50 hertz. Of course, everywhere this is omega t or theta. This is omega t or theta. So now what is applied here? This is 220 volt and 50 hertz. I am drawing it. It is a sinusoidal signal of, say, assume this to be of same amplitude and this much. Now, of course, this will be stepped down by this. Look at the, it says that the RMS value of this, it is 220 volt. RMS. I'll just tell this point. This is applied here. Now, this is being stepped down by this. I'm drawing it first, then I'll tell you. Suppose this is 0, this is pi, of course this is 2 pi, 3 pi, and so on. The same points I drop here. I'm dropping these points here. Assume these to be a straight line. Now, next I draw for this VI. I draw for this VI. See, this VI here, I am interested in this signal here, VI. This VI will be stepped down by this. Of course, it will be a sinusoidal signal. The function of this transformer is to either step up or step down without changing its shape. Means frequency and time period will remain the same. So, I'll get a waveform of this nature here. This is VI. What I obtain here is VI. Of course, this is pi. This is, sorry, 0. This is pi, 2 pi, 3 pi, 0 pi, 2 pi, 3 pi, 4 pi, and so on. Of course, with respect to omega t. And this is the waveform for this much. Now, rectification will start from here. And of course, the output which I'll obtain here will be a pulsating DC, and half wave will be rectified. Half of the wave will be rectified, and now my output will be something like this. That is, I assume this as the output current. Current across this load is I. Current across this load, suppose I say that the current across this load is I, and of course this will be working, we have already discussed. It is something like this. Omega t, 0, pi, 2 pi, 3 pi, 4 pi, and so on. Now, let's come to the problem. It says that a sinusoidal voltage of 220 volt 50 hertz is applied to the primary of this. This much voltage is applied here. Now what, look at this. When I say 220 volt and this much, it means this, whenever we say that, suppose at your home your supply is 230 volt, it is the RMS value always. In the previous problems, if you remember, a sinusoidal voltage of 220 volt peak value, if it is mentioned it is a peak value, it's fine. Otherwise it is a RMS value. Now my point is that what is the peak value of this? For any sinusoidal signal, remember that RMS value is equal to peak value upon root 2. So if I say that what is the peak value of this? The peak value of this will be 220 root 2. 220 root 2. Peak value of this will be 220 root 2. Now I am interested in the step down voltage of this. Now suppose this is Vs, I am interested in Vi. Can I say that Vs upon Vi, Vs upon Vi is equal to 10:1, 10 upon 1. That is, V1 upon V2 is equal to N1 upon N2. This implies that I'll get the value of Vi from here. The value of Vi, this is 220 volt. This is 220 volt. So Vs upon 10, Vi will be equal to Vs upon 10 into 1. What I have applied? V1 upon V2. I have applied here V1 upon V2 is equal to N1 upon N2. This transformer equation I have applied here. Vs upon 10. This Vs is given to 220 volt. This implies that the value of Vi which I obtain here will be, Vs is 220. So 220, I substitute this value. Vs is 220 here. 220 upon 10 will be 22 volt. Now since this 220 volt is RMS, it means the signal which I obtain here is 220 volt, and remember that this is not the maximum value, rather this is the RMS value. It means the signal which I obtain here at this point, the value of this is 22 volt RMS. That is most important to understand. Now suppose I say that what is the value of Im, since I know for this Im is equal to, for this, suppose I say what is the value of maximum current, I know that Im is equal to Vm upon Rf plus RL. My point is to find the value of this Vm here. The value of this Vm. Of course, the value of this Vm will be 22 into root 2. 22 into root 2. Remember that for a sinusoidal signal, if this is a sinusoidal signal here of period 2 pi, of course, if suppose I say if this value is Vm of this, for this RMS value is equal to Vm upon root 2. This you must have done in your previous classes. That for a sinusoidal signal which is of period 2 pi, its RMS value is equal to Vm upon root 2. So of course Vm, value of Vm will be Vrms into root 2. So this is what I am done, that this Vm, this is Vm, is equal to 22 root 2 upon this much. Now once you understand this point, rest is simple application of the formula, and it's a simple algebra that we have to apply. Now look at the problem. It says find the value of Im, IDC, IRMS. Simple. I'm sorry, this problem. Find the value of peak, RMS and average value of the output current. First part is this. You have to find peak value, means Im. You have to find peak value means Im of the output current. Then RMS value of the output current and the average value, IDC. These three things are required of the output current. Where is output current? This. It means I need this Im here. Very first thing, I need this Im. And this Im is equal to Vm upon Rf plus RL. Just try to understand that what I am finding. Im is Vm upon Rf plus RL. So this will be equal to, you can substitute the value. It is equal to 22 into root 2 upon 1000 plus 20. Rf is 1000, RL is 1000 and this is 20. So it is 20 plus 1000. This is the value of Im. This implies that Im is equal to this much ampere. I am not solving it fully. It's a homework for you to complete it and conclude to the final result. This is Im. Same part of the problem says find the RMS peak value I found Im, then RMS value of the output current. Now see, I am interested in the RMS value of this for a half wave rectifier, for the output of a half wave rectifier, since I know that IRMS is equal to Im by 2. IRMS, I am finding the RMS value of this. Remember that RMS value of this, it is, I say that the RMS value of this is equal to Im by 2. On the other hand, the RMS value of this is Vm upon root 2 or Im upon root 2. So I have derived the RMS value of this wave. It is a pulsating, it has AC component in it. So Im by 2, of course I have calculated from here, it will be this factor upon 2, it will be 11 root 2. Of course, 20 upon 2, this will cancel. It will be 11 root 2 upon 20 plus 1000, this much ampere. This part is clear. Next is IDC. So IDC you can find out. IDC is equal to Im by pi. Im is this much upon pi. This factor upon pi, you can find the value of IDC. I hope that this is clear to you. Next part is the input power and the output power. Input power will be AC. The input power which is applied here is of course AC. So PAC, input power, I'm writing here as IP as input power, that is PAC. Of course it will be IRMS whole square into RF plus RL. I have done this previously also with you. RF plus RL. You simply substitute the value of IRMS, that is IRMS is Im by 2. We have done this. IRMS is equal to this much. So IRMS 11 root 2. You can say that this is equal to 11 root 2 upon 1020. Alright, I'll make this as 1020. 1020. No, of course it will be 1020 whole square into RF is again 20 plus RF is 20 and RL is 1000. This much watt, W for watt. Next, input power and output power. Of course output power will be DC. Output is across this, so I can say output power is PDC. PDC is your output power, and that is equal to IDC whole square into RL. Output is only across this, input is this, because it has AC component. Output we say which is having only DC component. We are interested in that power which has the average DC power. This is the average value I told you, IDC or I average, when it is the same thing. So it is equal to this much. IDC, that is Im by pi. IDC is Im by pi whole square into RL, where Im is equal to this much. You have all done. This Im is equal to 20 root. Okay, I'll write it here. It is 22 root 2 upon 1020. I am writing this. Yes, this is Im upon pi into pi here whole square into RL is 1000 ohm. 1000, this much watt. So this is the problem that we have done. The very first thing was to understand the problem, and the main point in this problem, why I have done this problem with you, that it was given that a supply, a sinusoidal signal of 220 volt 50 hertz is applied here, and it is very important to understand that what do you mean by this much. This means that this voltage is RMS voltage. On the other hand, suppose I take one more problem that I did with you in the, suppose it is given here. Look at this problem. It is here, and it was given in this problem that this is equal to 100 sine 100 pi t. This problem I have done with you. This value was Vm. It is not the RMS value. What I have applied here is, you say that either it is a sinusoidal signal of 100 volt peak value, or you say it is applied, it is equal to this much. So whatever I obtain here will directly be the Vm. After this transformer being, after this voltage being stepped down by this transformer. But on the other hand, in this problem, this was the RMS value. So I initially, although it is not required, but I have just to make the problem very clear, that I have drawn this signal or the primary signal of this transformer, what is applied at the primary of this also. This maximum, this is the RMS value, and we obtain this as its maximum value for a sinusoidal signal Vrms is equal to Vm upon root 2. For this, RMS value is equal to maximum value upon root 2. On the other hand, for a half wave rectifier, it is maximum value upon 2, half of the maximum value. So it is generally a point of confusion among the students. So that's why I'm dealing with it. Of course, it has been stepped down by this, and from here I get the value of Vm. Once I obtain this Vm is equal to 22 root 2. This is Vi RMS. This implies that I write it here. This implies that Vm is equal to 22 root 2. Vm is 22 root 2, and rest is simple, just the application of the formula. So I'll stop it here. Thanks for the time being.